Hi and welcome back to my channel. Today we're going to be looking at practicing stereoisomers. First of all, I will give a brief overview about stereoisomers and then we'll try some practice questions. Stereoisomers have the same molecular formula and their atoms are connected in the same order. So this is different from structural isomers where they have the same molecular formula but they have a different structural formula. For stereoisomers, it's the spatial arrangement that is different, and we have two different types of stereoisomers. We have geometric stereoisomers and optical stereoisomers. For geometric stereoisomers, they have a lack of rotation within their structure. This can take place either where we have a carbon-to-carbon double bond or within a cyclic carbon structure. For there to be stereoisomerism, there needs to be different substituents bonded to each of the carbons in the part where there is the lack of rotation. Let's have a look at a carbon-to-carbon double bond. So here we have two hydrogen atoms, and on the other side we have two substituents R. Where they are on the same side of the double bond, this would be a cis isomer. If we have them on opposite sides of the double bond, this would be the trans isomer. If your substituents are on the same carbon of the double bond, there is no stereoisomerism. There's no way to switch these over to make something different. Okay, so they have to be on each of the carbons of the double bond. Where we have a ring structure, it's easier to show this with the wedges, which show that this is coming towards you, and the dashes, which show that it's going away. So this would be the trans isomer, where you have them on opposite sides of the ring, and then this would be the cis isomer, where they're on the same side of the ring. The second type of stereoisomer is an optical stereoisomer. These have four different groups attached to a central carbon, and they're arranged tetrahedrally. We call this central carbon a chiral carbon or a chiral center, and these molecules are non-superimposable mirror images, much like your hands. Okay, so you can have your hands match up if they're facing each other, but you can't get the palms of your hands to face the same way and have all of your fingers overlap on each other. These are then described as being asymmetric. Optical isomers are called optical isomers because they rotate plane polarized light. So this is just light where only one plane of light has been selected, and you can then rotate that using the isomers and measure it. Each enantiomer will rotate the light in opposite directions. One will rotate to the left and one will rotate to the right. They will rotate by the same angle. If you have a racemic mixture, this means you have 50% of each of the enantiomers, and therefore it won't rotate the plane polarized light, because one will be rotating perhaps 10 degrees to the left, the other 10 degrees to the right, so then they end up just being back at zero. There are different ways for us to draw the optical isomers. So here, if we have a structure with four different groups attached, you can either just switch over two of the groups that are attached to it to show the other enantiomer, or you can draw in a mirror and actually mirror the structure. Okay, so either way of trying to draw the other one is acceptable. Pause the video now and try this question. Here we're trying to find which of the molecules has a geometric isomer. So in this first one, we can see that there are two hydrogen atoms attached to this one. So we don't have any groups here for us to have opposite sides. For this one here, we've got two CH3 groups on this end one, and then we have this chain attached to this one. So this one can't have a geometric isomer. Here we have two hydrogen atoms, and then we've also got the two different chains, which could be either on the same side or opposite sides of a double bond. So this one will have your geometric isomers. Pause the video now and name these molecules. For this first one here, you need to count the longest chain. So we have 1, 2, 3, 4, 5, 6. So this is going to be Hix3ene would be the base of the name. And then we have two methyl groups attached to 3 and 4. and these are on the same side, so this is going to be a cis isomer. So cis 3,4-dimethyl-hex-3ene. For this one here, we have something based on cyclohexane. You have two chlorine groups attached, so this is going to be dichloro. And for naming these, you just choose one of them to be number 1 and then numbering to keep the numbers as low as possible. So we have 1 and 2, and these are both facing towards you, so this is going to be another cis isomer. So cis 1,2-dichlorocyclohexane. For this one here, you can see we've got the two chloro groups and they're on opposite sides of the double bond, so this will be a trans isomer. We have our carbons here, 1, 2 and 3, so this is based on propene. And we have chlorines on 1 and 2, so 1,2-dichloropropene, and they are on opposite sides, so this is a trans isomer. And then finally here we have two methyl groups attached to cyclopropane, and numbering again just to keep the numbers as small as possible. So we have 1,2-dimethyl cyclopropane, and they're on opposite sides. One's facing towards you and one is facing away from you, so this one is a trans isomer. Pause the video now and draw these molecules. So we'll start at the end of the name, so we have but2ene. So 4 carbons in a row, double bond on the second one. On 2 and 3 we have bromines, and it's a cis isomer, so they're on the same side. And then we can just go in and fill in the missing hydrogens on either end. For the second one, we're starting with cyclopentane, so pentagon. And on number 1 and 2, we have methyl groups. So this one here we'll put towards us, and it's a trans isomer, so the other one will be facing away. Pause the video now. Why does this molecule not have geometric isomers? So the two groups are attached to the same carbon of the double bond. This means that you can't have opposite and same sides of the double bond because they're on the same end of the double bond. Pause the video and try this question. For identifying chiral carbons, you want to have a look at each carbon in the structure, and you're looking for one which has 4 different things attached to it. So for the first one, it's quite easy to see. We've got this carbon in the centre with a hydrogen, an NH2, C2H5, and then a COOH attached. So we'll put a little star beside that one. In this one here, you can see this carbon has 3 hydrogens, so that one can't be a chiral carbon. This one has 2 hydrogens, so this can't be a chiral carbon. This one has an OH, an H, a CH2OH attached to it, and then a CH2CH3. So this one is a chiral carbon. And then this one here has 2 hydrogens, so this one cannot be a chiral carbon. When it comes to looking at skeletal structures, sometimes it can help to put in where the hydrogens would be. I'm just going to put them in as dots. So this one would have 3 hydrogens, so cannot be a chiral carbon. This one would have 2. This one would have 2. This one has all 4 bonds already used. This one here would have 3, would have 2 on this one, and 3 on this end one. So this carbon here in the centre has an OH group, a CH3, a C2H5, and a C3H7. Therefore, this has 4 different groups attached to it. Looking at this structure here, we have a ring which can complicate trying to find the chiral carbons. So we'll add in the hydrogens onto each of the carbons just as dots so we can see them. So we can immediately eliminate these ones here because they each have 2 hydrogens, and this one here because it's got 3. And we can have a look at these 2 here. So this one has a hydrogen attached, a CH3. It then has this ring here which attaches round. You can see it's got this OH, so there's no symmetry on this. And then going this way, it comes round to this carbon with the OH. So this one can be a chiral carbon. And then the same thing's happening here. We've got an OH, an H, and then goes round this way on the ring and this way on the ring, and there's no symmetry through here. So this one is also a chiral carbon. And then this structure here is much larger. So we have 2 hydrogens attached here. We'll have one here, one here, one here, one here. On these parts here, we're going to have one here. There'll be none here because this carbon's got 4 bonds, and so does this one. We'll have one here, and then again none here because this carbon's got 4 bonds. So going around each of the carbons that we can have a look at, this one is not chiral. This one here, we have an H, we're bonded to an O, this part of the ring, and then this CH2OH. So this one will be a chiral carbon. This one here is attached to an OH, it's attached to this part of the ring, this part of the ring, and an H. So this one is also a chiral carbon. Similarly for this one here, and for this one here. These ones here cannot be chiral carbons because they only have 3 things attached. Okay, they need to have 4 to be chiral, so those ones can't be chiral. Pause the video and try this question. So here we're drawing the other enantiomer for each of these. So we can either just flip over any of the 2 parts of the molecule, or you can draw in a mirror. I'm just going to draw in the mirror. So just mirroring exactly what is there, including the shapes of the bonds. In this one here, we can just swap over any of the 2 groups, and the easiest way to do that is to look at the ones with the wedges and dashes and just pick one and change it to be the opposite one. Pause the video and try this question. So here we have a problem solving question. If you have 100% of A, then you'll get a rotation of 20 degrees to the right. If you have 100% of B, you'll get a rotation of 20 degrees to the left. If you were to have 50% of A and you were to have 50% of B, then overall your rotation would be 0 because they would cancel each other out. Here we have a rotation which is going 10 degrees to the right, which means that we must have a mixture of the 2, but that we've got more A than we do B. So in the mixture, we know that we have to have 2 parts which will be cancelling each other out to give the 0, and then there must be an excess of A, which is giving the 10 degrees rotation to the right. So we need to work out what the proportion would be to give us that. So because we have our degrees, which is half of what the original would be, if we have 75% of A and 25% of B, then the 25% of the A and the 25% of B will cancel each other out, leaving 50% A left over, which will give the 10 degree rotation to the right, which is the excess that we would see. Thank you for watching my video. I hope that you found it helpful. Please remember to subscribe and ring the bell so you can be notified about new videos. You can also follow me on Twitter at Miss Adams Chem and Instagram Miss Adams Chemistry for updates on new videos and flashcards throughout the year. Bye for now.